Welcome to Brain Vision.
Hi everyone, so what we have is copper wire with a diameter of 5 millimeters, a density of 8950 kilograms per cubic meter, and a specific heat value of 0.383 kilojoules per kilogram degree Celsius. And what's happening is this copper wire is being extruded from a temperature of 350 degrees Celsius, and it's cooled to a temperature of 50 degrees C in air that's at T equal to 25 degrees Celsius. What we're asked to solve for is the total heat transfer, rate of heat transfer from the wire, if the wire is moving at 8 meters a minute. First thing we're going to do is write down our assumptions. So we are going to assume that this entire process is at steady state, so conditions will not be changing with time. Next, what we're going to do is also just write down the properties of our wire. So we know that the density of this wire is equal to 8950 kilograms per meter cubed. And we also know the specific heat value of copper is equal to 0.383 kilojoules per kilogram degree Celsius. So next what we're going to do is we're going to use this information about the density and the velocity that this wire is moving at to solve for the mass flow rate. So what we can do is we can say that m dot is equal to rho times v dot, and v dot is the volume flow rate. We can expand this to say that this is equal to rho times the cross-sectional area times the velocity that this wire is moving at. And we can further go ahead and say that this is equal to rho times pi r0 squared times velocity. Recall that we are given the diameter, so we know the radius, we know the density, and we know the velocity that this wire is being extruded at. And we can calculate the total m dot to be 0.02343 kilograms per second. Next, what we can do is do our energy balance. We're going to be taking the wire as our system. So what we can do is say that the total energy coming in is equal to the total energy coming out. And this is because we're at steady state, so the total energy within the system is going to be equal to 0. Now we can expand upon energy in to say that this is equal to m dot h1, and we can expand upon energy out to say that this is equal to the total rate of heat transfer plus m dot h2. Now solving for our q out, we'll see that q out is equal to m dot h1 minus h2. Now using the definition of enthalpy and specific heat and temperature, we can say that this is equal to m dot Cp T1 minus T2, and that's equal to our total heat transfer. And we actually know all this information. We know the m dot of the wire, we know Cp, and we know the temperatures that we're starting at and we're ending at. So by plugging this information in, we get a total heat transfer equal to 2.69 kilowatts. And that's our final answer.